Hi everyone, my name is Matt Buford. I did my research project on artificial intelligence MRI imaging. A little bit of introduction. MRI, as we all know, is one of the leading radiographic modalities we use today. It's used in many musculoskeletal injuries, disorders, and pathologies. It does have its drawbacks, though. Our scan times and our image acquisitions are long. It requires our patients to remain still for extended amounts of time, and if they move, they could extend those scan times even longer or create artifacts for us. So recently, researchers have been studying how they can use AI or artificial intelligence to help things like reduce our scan times, increase our image reconstruction and acquisition times, and even help finding pathologies to help radiologists with diagnosis. So what questions should we ask? Does AI or AI-assisted MRI increase our effectiveness with the modality? Does it help? Will its implementation improve on our patient's experience? And can or could its integration negatively affect our images or diagnosis? So one of the first teams I found was a team of researchers at MIU, Grossman School of Medicine. They use, in conjunction with Facebook AI, they created a neural network, and they called it was as part of their FAST MRI initiative. During the study, they taught the neural network how to read and assess the images, and towards the end of the study, only with 3/4 of the amount of data normally used to create an MRI scan, the network was able to recreate those scans. With these results, they were really excited and they decided to test them on working radiologists. Over a series of months, the radiologists participating in the study were given 2 sets of images that they couldn't tell, they didn't know which one was which, of traditional MRI scans and MRI scans created by the FAST MRI network, and with no significant differences were found in the abnormalities that the radiologists discovered or their diagnoses that they reached. AI-assisted images were actually preferred in quality over the traditional scans by a majority of the radiologists in the study. With these findings, the researchers at NYU were really excited, and they made the initiative open source so that others could contribute and help the network learn. Another team at MRI and Harvard set out to improve our reconstruction processes of MRI images and data reconstruction. They used current generation graphic processors and created an automated reconstruction process using the machine learning of the network they created, and they named it AutoMap. The team working on the project used over 50,000 brain scans to train the network using, I believe, 2 different databases to feed the network its images. AutoMap's images not only had a better signal-to-noise ratio outputted, but yielded better images with less noise overall after reconstruction. The image reconstruction was only milliseconds on average as well, and the team was really excited to get to a point where they could introduce AutoMap to our current work, like MRI workflows, to reduce our scan times and procedure times. Another way researchers are using AI to help our MRI process is a network called a convolutional neural network. These were originally developed to help classify and organize images. It's a deep AI on a network of computers, and it's over time it's shown and given millions of images to analyze and read. Its AI learns with great accuracy what the images consist of, including shapes and colors, subject matter, lines, and grayscale images. And you can see on the little sample I have here, the CNN network took this image it can read images like this cat and figure out that with 70% accuracy that it believes that this is an image of a cat instead of a dog or a tree, which is crazy. It can also, with that image, it can actually output or process what it believes the image would look like if it was color instead of black and white, which is also amazing. So with this promising AI network, researchers realized the diverse impact that this type of AI technology could have on medical imaging. They fed these networks with tons of images of different planning on different applications and studies. Some of them that we're going to talk about are like a computer-aided diagnosis for Alzheimer's disease and prostate cancer, a reconstruction of accelerated MRI images using the CNNs, and even case-based filling techniques for image reconstruction. And this is like an example of kind of what it can do. You can input, or you can give it an input of this black and white image of a butterfly. It can output what it believes the colors of that image would be. It can do things like you can give an input of what this landscape would look like in spring, and it can output what it believes it's going to look like in winter. And then this is like their MRI example where they gave it an input of a low sampled knee MRI, and it outputted what it believed that MRI would look like if it was fully sampled. And there's a little bit of like data consistency example here as well, which is really cool. So one of the first studies that researchers were doing with the CNNs, they did some brain studies. Brain studies were performed using Alzheimer's disease or AD patients classifiers, and with the AI assisted MRI. And the study showed that it found patients with abnormal features were identified 2 years prior to their definitive AD diagnosis, which is great for early onset Alzheimer's recognition. It was better than 80% accuracy with a sensitivity and specificity rate of 87% in the diagnosis. The AI was better at that. And then our traditional methods in MRI data alone sit at around 72 accuracy, 69% sensitivity, and 70% specificity. So that was a pretty big increase for them. It's very promising to aid radiologists in early diagnosis for early onset Alzheimer's disease. Another way they're using this CNN networks in diagnosis or prognosis is they used a CNN to assess the need for dynamic contrast enhanced MRI for prostate cancer patients. And after the study was finished with a 94% sensitivity rate, the CNN was more accurate than the practicing radiologists that participated in the study, sitting at a 89% sensitivity rate. So using the CNN or the network to help analyze and read the images you're showing it, it's great for this application to be used in conjunction with radiologist expertise, and it could prevent individuals from having to undergo the DCE MRI procedure when the cancer was ruled out, or they didn't even need that procedure being done. Some of the main ways that these convolutional neural networks are being used is an image-based technique, and image-based techniques used in reconstruction of accelerated image acquisitions, so like fast MRI scans. Similar to the way we use zero filling technique. A learning variational network was taught by the CNN to a learning variational network is used to fill this undersampled case space by enforcing its own data consistency around it, so it reads the images and knows what they should look like. It uses the convolutional neural network to base its learning off of. So using that network and what it's learned about fully sampled images, the VN network reconstructs the accelerated MRI image to a near 1-to-1 ratio of accuracy up to 0.96. And you can see the example I have down here. It starts out with the reference image, and then the zero filling technique gives it about an 82 or 0.82, close to 1% image reconstruction, but the learning variational network gets up to 0.96 or 96% accuracy. This team is really excited because this method could really open the door for drastically shorter scan times if it's implemented correctly. A case-based technique is also being researched. The robust artificial neural network of case-based interpolation, or what that team calls Reiki. It's a machine learning method to improve case-based interpolation, something that we already do in MRI. So the Reiki team uses our fully sampled center case space to interpolate the rest of the undersampled data points, which is something MRI already kind of does. But learning from the CNN, its reconstructions are consistently better than our own traditional methods like parallel case-based filling. The only drawback is the method the neural network has to train itself in real time, so this process does take longer. Oh, and these are some examples. Maybe my video is kind of over it, but you can see this is the Reiki and the reproduction 1, 2, and 3, and they're the 2 is higher than the parallel case-based filling. So in conclusion, AI and MRI does have a bright future, with everything to reducing our scan times with CNN accelerated image techniques, using machine learning software like AutoMap to reconstruct images with only half of the data that we normally use in a typical MRI scan, to even aiding doctors and radiologists of diagnosis for early onset Alzheimer's disease, years ahead. There are some drawbacks. A lot of the studies, the control groups are limited. The numbers are still in the hundreds and thousands instead of hundreds of thousands. But AI-assisted MRI scans aren't too probably far off in the future. Before long,